Hi there. In this video lesson, we're going to look at the physics of rolling objects, and the question that we're going to answer is how are the kinetic energies of translation and rotation related to each other? And we'll try to keep it real here with an example that should make sense to you. So let's look at this picture. You want to sketch this. And let's say that you've got, like, say, I don't know, why don't we call this a pool ball? Okay. And let's say that the pool ball is just rolling across the table. Okay. So you got a nice solid sphere, and you would say that the sphere has a center of mass velocity because it's traveling from left to right. But you also would observe the pool ball rolling, so it's going to have an angular velocity, and it looks like it's going to be rolling in the clockwise direction. So the deal is that this pool ball really has two types of kinetic energy. It's got translational, because it's moving from left to right, but it also has rotational. Because it's rotating. So the question that we would want to answer about this, I don't know, would be something like this. Let's say that you know, so example, what if you know that the translational energy is equal to 5 joules? You know, let's say that you calculate this, right, and you get 5 joules. If you know that, then how much energy goes into rotation? Okay, and I hope you're not just jumping and saying, oh, it must be 5 joules. There's no reason to assume that. You know, this could be something quite different, and we want to have some way of predicting what's happening here. And there should be some relationship, because if an object is rolling, obviously how fast it's moving from left to right is going to depend on how many rotations per second it's making. So there should be a good answer to this question. All right, so we're going to come back and we're going to answer this as our example, but we're going to have to do a little bit of theory here off to the side. So let's think about this. Let's think about the object rolling. And if you were looking at the object from the side, from the Earth, then you would say from the Earth frame, meaning from the Earth frame of reference, you would observe that this object is moving from left to right. And you could probably measure that velocity, the center of mass velocity, using a photo gate, like we did in the activity. Okay, so this is pretty easy to get. So this we get, right? So the center of mass is moving with the velocity. Now, when you think about the rotation, it's easier to think about rotation from the point of view of the center of mass frame. Now, what does that mean? Well, that means if you were basically shrunk down and you were living at the center of mass of this pool ball, to you would be at rest because you're the origin. But if you look around you, everything else is going to be moving. So if I was living at the origin and I looked up, I would notice that this edge of the ball is moving with some tangential velocity to the right. The reason is because the ball is rotating. But from my point of view, I see that tangential velocity going that way. Now, if I look down, if I look at where the ball would be touching the ground, I would notice that the tangential velocity is going in the opposite direction, because that's what tangential velocity does. Okay, so these tangential velocities really have the same value, because we're not speeding the ball up or anything, but they're in opposite directions. Now, you're probably wondering, well, why do we think about it this way? Well, here's the deal. If this ball is going to roll, and it's not going to slip on the table, but it's always going to be just touching the table and lifting off, this velocity and this velocity have to be equal. the center of mass velocity and the tangential velocity have to be exactly the same. So for rolling without slipping, the tangential velocity of the outer part of the wheel must be equal to the center of mass velocity of the center of the wheel. This is not always easy to accept or to visualize, but let me just have you think about this. If you're driving in your car at say 65 miles per hour, then the 65 miles per hour is referring to the center of mass velocity. The axle of your car is traveling down the road at 65 miles per hour. Now, in order for that to happen, your wheel obviously has to be rotating, but you want the wheel to rotate so that it's rotating just fast enough so that as the rubber comes down and meets the road, it's traveling at the same speed so that you don't skid. Okay, so what I'm saying is that the tangential velocity down here, if this is a car tire, it has to match the center of mass velocity of your car. If it doesn't, your tire is going to slip and you're going to be burning rubber, literally. Okay, so this is a really important statement. For rolling without slipping, you assume that those velocities are equal, and you might have to think about that a little bit more, but that's important. That is going to let us get to what we want then, in terms of our energy ratios. So I'm now going to use this, and I'm going to figure out the ratio of rotation to translational kinetic energy, so we can answer the question that we put out there. I'm going to fill in the formulas. Okay, so you should recognize those. I'm also going to do a little bit of canceling. And then I'm going to do some substituting. And the first thing I'm going to substitute is for I. And I'm going to replace I with C times mr squared. And again, C is the shape factor. So we can have a shape factor. I'll put this on the side. Remember, that's the thing you have to look up usually. C is greater than 0, less than or equal to 1. So we got to remember that. And then for omega squared, I'm also going to do a substitution. And here I'm going to be substituting the following. I'm going to take omega, I'm going to replace it with tangential velocity over radius. Okay? Now, you're probably going, what? So, I want to remind you, all right, recall, in our earlier part of this unit, we learned that you can always get a tangential motion quantity by multiplying the angular quantity by the radius. So that's exactly what we can do here. And of course, if you solve for omega, you have to divide both sides by r. And so that's a very clever little substitution there that we're going to do. Before I forget, I'm going to write the bottom part in here. And now I'm just going to go crazy with canceling stuff. Okay? So masses cancel out. R squared cancels R squared. V center of mass squared cancels V tangential squared. Remember, V tangential and V center of mass are the same. So these actually go away. And this is really beautiful because so much stuff cancels here, and the only thing you're left with is C. So at the end of the day, we get a real simple result, which is that the rotation to translation kinetic energy ratio is just equal to the shape factor. That's a big deal. And it's simple to remember, right? It's just, you just have to remember that it's R divided by T. So it's kinetic energy for R divided by T. But that's just going to be the shape factor. Now, that's should be realistic. What it means is that for shapes that have a big C value, like a hoop or anything that's hollow, what that means is that you're going to have more rotation, less translation, right? Your ratio of rotation to translational joules is going to be bigger when you have shapes which have their mass on the outside edges. And that's because more of the energy is going into spinning the object and less is available for making it travel forwards. So if you want to think about it, that's kind of like the conceptual part behind this. Otherwise, that's actually the formula. So finally, let's go back. Let's see if we can use it in our example. We said if you have an example here where the kinetic energy is 5 joules, what's the rotational energy? Okay, so we've got KER over KET is equal to C. We said this is a pool ball. Pool ball is a solid sphere, so C is going to be equal to 2/5 for a solid sphere. And so we'll have KE rotation over 5 joules is equal to 2/5. And yeah, I picked easy numbers on this one because you can see that, you know, if this is your variable, over 5 joules equals 2/5, right? That means that you have 2 joules of rotation. That's what you got. And so now we know. So if it's 5 joules of translation, you've got 2 joules of rotation. So you can imagine, you know, different shapes. If I picked a bicycle wheel, for a bicycle wheel, C is equal to 1. So that would mean I'd have 5 joules of translation and 5 joules of rotation. So I would have more energy with rotation in that case, right, for a hoop. And so it makes a difference what the shape factor is. And so what I want you to think about is the more that you have, the bigger your shape factor is, the more rotational energy you're going to have compared to translation. All right, hopefully that helps you to understand that. That's a really important result. See you later.